Awesome. All right, hi everyone, welcome back. Today is an exciting day because we have our first guest lecture. And it's my pleasure to introduce Jason. So Jason is a PhD candidate at UC Berkeley. He's working with Professor Kaushal Srinath and Professor Claire Tomlin. And Jason finished his undergraduate studies in mechanical engineering at Seoul National University. His research interests center on optimal control, both their theory and application, nonlinear and hybrid systems, data-driven methods for safety and control, and in general, their application to autonomous robot mobility. And with that, Jason, feel free to take it away.
Yeah, thank you for the nice introduction, Andrea. And hi, everyone. Nice to meet you. So today I'm going to talk about safety filters for uncertain dynamical systems, control theory, and data-driven approaches. And I've heard that this is like the designing safe controllers is actually one of the main themes of your class. So I'll not try to spend too much time on the motivation, but I do want to highlight that the main reason why I investigate safety problems for robot autonomy is because these days the state-of-the-art autonomy achieves a lot of cool things like cool tasks, and but they still lack a lot of guarantees. And this actually is a little bit unfair to use Boston Dynamics video to highlight this point, because the video is a little bit obsolete now. But still, like, this makes my point that a lot of the people spend a lot of time developing controllers to do specific tasks, and these tasks can be really versatile. But then like, even after spending a lot of time, we lack a lot of tools that provides a very rigorous guarantee for these systems. And that is the main motivation why I investigate safety problems for robot autonomy. And what is special about this modern robot autonomy system compared to classical control systems? And I think there are so many aspects. Like, for example, I think the interaction with the environments or other agents is also one of the central topic of Andrea's class. But today, the 2 points I want to highlight is that one, that this new robot autonomy, they usually deal with more complicated and uncertain dynamics. So, for example, like robots or like modern new generation aircrafts. And usually they also involve a lot of data-driven components in their pipeline. So data-driven components are more common for prediction and perception, but I think it'll be essential to be incorporated into the control or decision-making part of the autonomy as well. And I'll talk more about that later. But assuring safety for data-driven kind of control method is still like a underexplored area. So I think this is why the research topics in this domain of like providing safety guarantee for this robot autonomy is a really challenging and also timely topic. So today my talk is divided into 2 parts. The first part is a more tutorial-like part, and the second part is a more researchy part. In the first part, I want to go through various methods of control theoretic designs of safety filters. But I think due to the time limit, I want to mainly focus on the control barrier functions, because I've heard that Andrea will be covering Hamilton-Jacobi reachability. She has already covered reachability part a lot, and since I think CBF is also a very kind of popular safety filter method these days that one can quite easily use. So I want to mainly focus on the control barrier function, not because it's my favorite method, but I think it would be useful for the class. The second part, I'll introduce 2 specific kind of data-driven filter, safety filter design that I worked on during my research. One is based on the Gaussian process regression, and the second one is the notion so-called discriminating hyperplane that we recently published. So this will be focusing more on how we combine data-driven methods with the safety filter design. So before I jump into the main content, if there's any questions, I can see all of you. So if you raise hand, then I'll be happy to pause my presentation and take questions. So let me know. So the first talk will be the control theory design of safety filter, and this part will be based on the tutorial paper I wrote with my collaborators, so Kim and Melanie from ETH, and Andrew and Professor Nannings from Caltech. So what is safety filter? And you all might be already be familiar with this concept, but let me just recap. So safety filter is a module in the control system that takes in the state information and the desired control information and checks whether the desired control is safe or not. And if it's potentially unsafe, the safety filter would override that desired control action with verified safe action. That's the role of the safety filter. And the nice thing about this separated out module concept is that it decouples performance and safety. So the decoupling between, like, if the designer tries to achieve performance and safety at the same time, it will complicate the design process a lot. And that's why the safety filter design is the design process a little bit. So the designer that focuses on the task controllers can only focus on the task control, and the safety filter designer can only focus on the safety filter design. And I'll not claim that this is ideal kind of framework. Like there might definitely be situations where you have to consider like performance objectives and safety objectives altogether. But at least in the talk, this is a framework that decouples the performance kind of objectives and like separate it out away so that we can only focus on the safety problem here. So that's why kind of we will mainly use the language of safety filter framework. And so this is like a mathematically formal description of what the ideal like safety filter would do. And of course, this is not the like very objective formulation. There can be many other ways of thinking about the safety filter problem. This is just one way of it, but it captures the core ingredients of the safety filter. So first, like although it mainly tries to guarantee safety, like it is a filter that filters the desired control. So there should be some notion that it should minimally deviate from the desired control. So that's in our objective function here. And then the control action that the safety filter selects should always be contained in the admissible control signal. And the most important thing here is that the trajectory should always satisfy the target safety constraint. And the main difficulty here arises from the fact that usually we don't know how much long the trajectory should satisfy the safety constraint. So in other words, this safety the trajectory might have to satisfy the constraint indefinitely. So because we don't know exactly the time horizon, this could become like an infinite time horizon problem. And so like how like in what domain we can guarantee safety this for infinite time horizon will be a crucial kind of problem to solve to design these filters. Before I move on to the next part, is everything clear with this kind of definition? Okay.
The students are experts. They're good.
Great, nice. So we can think about the filter design problem into two components. The first component is the safe set synthesis. So the main challenge arises from the fact that we specify a target domain that where our kind of robot state wants to stay inside. The problem arises because not all states in the target domain is safe. And I guess if you already took if you already learned about reachability, I guess you understand why this is. But there are like part of the state space where you start from there or you end up being there, like you will be inevitably always reaching to the failure region, whatever you do with your control action. So we have to rule out those regions. So we have to like define or verify a subset in the target set that is safe. So that's the kind of domain problem. And once we verify this safe domain, And then we, of course, have to design a control signal such that the trajectory under that control signal will be actually staying inside that domain. I see some thumbs going up. Is it Andrea, you, or is there like a question?
Any questions?
Okay.
I think we're good.
Okay, nice. I saw some thumbs up in that screen, so in that view. So okay. So I'll talk first about the safe set synthesis, and I guess again you might be already be familiar with this concept, but let me just quickly recap. So usually, because of the infinite horizon nature, we want to verify a domain where the trajectory can stay like indefinitely for a long time. And such a set is called like invariant sets. And this is the core concept for safety filter design. So the forward invariance definition is that a set is forward invariant if for any initial state inside the set, you roll out the trajectory and the trajectory stays indefinitely inside the set. So if a set satisfies this property, it is called a forward invariant. Here, like since we have to check every initial state, it might seem like this is a very difficult condition to check given a set. So how do we check the set is forward invariant? And actually the answer is not too tricky. Like basically we don't have to check everywhere inside the set. We only have to check at the boundary condition of the set. And we use like a distance-like function h to do this. So let's say we constructed the distance-like function of the set, and so that the set S is the zero super level set of this h function. Then if at all points on the boundary, h dot along our dynamics, if h dot is greater or equal to 0, then it means that the trajectory following our dynamics will never go below 0 where h is 0. So it means the h value along our trajectory will always be positive. So in this way, we can kind of easily check the condition of forward invariance. And we will similarly extend this notion to the control system. Here, I'm introducing this notion for autonomous system where there's no control signal. But but if you go to the control system, we will just extend this forward invariance notion to the existence of the control signal. So for any initial state inside the set S, if there's a control signal that drives the trajectory to stay inside the set indefinitely, then the set will be called control invariant, meaning anywhere from inside the set, you can always make sure that you can maintain the trajectory to stay inside the set. And again, the condition I described before, I'm not sure if I mentioned the name of the theorem. This is called Nagumo's theorem. That all you have to check is the boundary condition that h dot has to be greater or equal to 0. You can similarly extend that notion to the control system. The only difference now is that instead of h dot always satisfying greater or equal to 0, you just have to check the existence of such control input at the boundary. So if this condition is satisfied here, then you can guarantee that whenever the trajectory hits the boundary, you make sure that the control satisfies this h dot condition, and therefore it remains inside the super zero level set of the h function. So it seems like this h function is really important, right? And this is kind of the if you can find such h function, and that naturally also gives us a good way of constructing a safety filter design. So a general procedure of how we design safe controller or like safety filter is first we will get this safety specification. So in other words, the target region where we want to stay inside. This is the white region here in the figure. And then we'll verify a control invariant set contained in this set as X. So the control invariant set will be called S in my talk. And this is the safe domain that we verify to be safe, and then we want to stay inside that set forever. And once we verify this control invariance of the set, what we'll do is we'll design a safe controller associated with this set so that the closed loop dynamics under the set S, closed loop dynamics under that controller will render the trajectory to be render the closed loop dynamics trajectory to be forward invariant and stay inside this set. So, this is almost the most generic pipeline of designing the safety filter. And I think you learned one method of doing this, which is the Hamilton-Jacobi reachability. So I'll go to that part, but I'll maybe give you just a quick overview because I want to spend more time on the CPF stuff. So reachability, like this is a very systematic way of constructing such safe set. And how do we do this? We define our failure region, the outside of the target set. So this might be a little bit confusing, but we define this as our target set. So this white region is our desired state region, and we define the failure region as our target set. And then we compute the backward reachable tube of this failure region. So we set this target set and then compute the backward reachable tube. And then the backward reachable tube we compute here from anywhere inside this backward reachable tube, no matter what you do with your control, it'll inevitably hit the failure region. So that's why I call it an inevitable backward reachable tube. So once you compute this inevitable backward reachable tube, the complement of this set is called the finite time valuable kernel. And this finite time valuable kernel is the region where there always exists a control signal that can guarantee to not hit the failure region. And if you do it for a long enough horizon, I'll skip all this part. You will get a infinite time valuable kernel, which will be the maximal control invariant set contained in your desired state region.
Jason, can I quickly interject? So
yeah.
If you just remember, like when I defined like the BRT and we did the dynamic programming principle, so far I was always talking about like 0 to big T as the time horizon under which we compute, but you can run big T to infinity. And under certain conditions, your value function converges. And this is what Jason is describing here.
Yeah.
You get a value function that no longer depends on time.
It's a really good point. So actually, convergence is an issue here, but I'll not talk too much about that today. But you have to make sure that the value function converges, and so that the value function doesn't have the time notion anymore. And if the value function converges, then the 0 level set of this value function will give you the maximal control invariant set. So now you got your safe domain. And you can design a least restrictive reachability safety filter based on this. So basically, this safety filter allows the desired control signal to do whatever it wants, as long as it is strictly inside the verified state set. But then if it's very close to the 0 level boundary, then it switches to our reachability optimal control. And this is a quick example. So this is an inverted pendulum, and our desired safe region is the angle range around the unstable equilibrium from minus 0.3 to 0.3 radian. And we have some unsafe desired control signal. So it does some kind of bang crazy control that will quickly shoot the pendulum outside of the region, outside of our safe region. And then after 6 seconds, it will come back to the origin using like feedback linearization controller. You'll see that this is a phase portrait of the system in theta and theta dot space, and you can see that the trajectory quickly exit the desired defined safety region. So let's see how the reachability controller can filter this unsafe input. So in figure on the left, I additionally add some velocity range here. And we define the target set as the region outside of the box region. And then we compute the Vowel kernel. And the Vowel kernel, after we compute the infinite horizon Vowel kernel, the infinite horizon Vowel kernel looks like this diagonal shape. And then we kind of set the control signal to our optimal reachability control whenever the trajectory hits the boundary of the safe set. And then you can see that the trajectory starting from this initial state doesn't not exit our Vowel kernel, our maximum control invariant set. It stays along the boundary of the set, and then it stays inside the set, and then so on, so that it eventually stays always inside this Vowel kernel and then becomes safe. And this is the control signal of the reachability. The red one is the original unsafe control, but the reachability kicks in. The reachability controller kicks in whenever we have to override the control. So this is how we do with reachability and what you have learned in the class. The main downside of this design is this switching-based design is not very practical because we usually don't want to apply this type of chattering control to our physical system. And the physical system also kind of there's like a delay, and these physical limits kind of usually would break down the mechanism of this switching control. So that's where the idea of the control barrier function emerged. Before I go into the CBF, any questions in the reachability? Okay. So whether then we impose a hard stop condition at the boundary, like overriding with our optimal safety control at the boundary, and we smoothly break the trajectory as it approaches the boundary. That's the main motivation for the CBF-based design. And you can actually do that with this kind of comparison principle. So so if you go back to the reachability safety constraint, here, this condition here, always ensure that V dot is greater or equal to 0. So that's why we only impose it on the boundary. But in the CBF definition, we will kind of extend it a little bit. We will alter it a little bit, and we will add this additional term here. So what this additional term do is, if we evaluate our value of B, the control barrier function value, along the trajectory, it'll stay above the curve that is defined by the equality condition, B dot equals minus gamma B. And that equality condition gives an exponentially decaying curve. So if the trajectory started from a positive value, then this trajectory will always, the value of the CPF along this trajectory will stay above this exponential decaying curve. And therefore, always it'll be a positive value. And since our safe set is a super zero level set of the CPF, it'll always stay inside our safe set. So the CPF definition is a function that for every state inside the set S, this condition is satisfied. This is like just a terminology, but we'll call this constraint here as a barrier constraint, and we'll call this plus gamma B term as a comparison function. So the main theorem is basically just what I said. If there's a valid CBF, and if the safe control signal, if the control signal satisfies these barrier constraints every time, then the set will be rendered forward invariant under this control signal. I'll skip the proof, but the proof actually is derived from the Nagumo condition, because this boils down to the Nagumo condition, the same Nagumo condition when B, the value of B becomes 0. And let's see one specific kind of case where the dynamics is affine in control. And like this affine form of the dynamic is very common for a lot of robotic systems because we can derive the dynamics of the robots from the Euler-Lagrangian equation like this. And the F term is called the drift term, and the G term is called the excitation term or the control vector field. So if our dynamics is control affine like this, the barrier constraints will have a structure that is affine in U as well. So if we incorporate that as a constraint in a min norm control objective, then this becomes a quadratic program. And since quadratic program is and this is a very compact kind of quadratic program, for example, compared to like predictive control, MPC. So these are very compact quadratic program that can be solved super fast in real time. And that's one of the reasons why CPF became really popular these days as a safety filter design mechanism. Just a quick notation in case you're not familiar with this. LFB means the gradient of B times our dynamics. So this is a Lie derivative, which also appears in the Hamiltonian of the reachability. So this LFB plus LGB is the evolution of our barrier function along our dynamics. This is actually a little bit important for the later part because you can see that we use the information of our dynamics, F and G, to construct this barrier function constraint, the barrier constraint. Just a quick note that if there's something invisible, you can relax the constraint. This is a very common technique for practical deployment because like if the solver is invisible, then we still have to give some control to make some control input. And the another point is that if there's no control bound at all, then if there's only a single constraint, then we can come up with a closed form solution for this filter. So the crucial design step, this will be a little bit of a recap, but first, the CPF that we use or the CPF we design has satisfied these two conditions. One is that the super zero level set is contained in our target set, and it has to be control invariant. The second, the gamma, the what value of gamma we choose kind of decides the profile of the smooth breaking. So if we use a too small value of gamma, then it can, like the breaking would kick in more earlier, but then it might be too restrictive. Whereas if we choose a larger gamma, that it might be less restrictive, but then it might be too aggressive. Like as it approaches the boundary, the filter kind of might kick in too aggressively. And you will see that behavior in a minute. So here we come back to this inverted pendulum unsafe control signal example. Now we design a CBF here using following a very Lyapunov-like method. So we use this quadratic form of the control barrier function, and we check whether the CBF constraint will be feasible or not. And based on this checking, we can determine a valid parameter for this design, A, B, and the gamma value that makes the CBF valid. And this procedure can be done more kind of in the generic way using a like optimization formulation. I will not go into that today. But here you can think of this as some Lyapunov-like function. So Lyapunov function looks like a bowl shape. So you flip it and then you like make an offset so that the zero level set emerge, and we can use that zero level set as our control invariant set. Now, so we choose a small gamma value here, 0.2 to 0.2. The blue level set, the ellipse, is the zero level set of the CBF. And you can see that the filter kicks in nicely and then it smoothly, so that it never actually hit the boundary. It smoothly approaches the boundary, but it never hits the boundary. And then the CBF value always stay positive here. If we choose a slightly larger value of gamma, let's say 0.2, then you can see that the trajectory is allowed to approach the boundary much more aggressively. But it is still much more smoother than how the reachability safety filter kicks in. And you can see that now the CBF value gets almost very close to the zero, but it still stays positive. So we can guarantee safety with this. So this is how the CPF, basics of the CPF design works. And I'll like move to the next part. Yeah, I see the question and the.
Oh, hey,
Yeah.
Jason, can I ask a question?
Yeah,
I'm
go ahead.
I'm just auditing this lecture. This is thank you so much. So I wonder here, how do you incorporate the -3 to 3 control actuation limit? Are you putting it part of the QP or like?
Yeah, I'm putting it as a part of the QP. So here the actuation limit is set to the control bound is set to ±3. And in the CPF design, we check whether this CPF condition will be satisfied with this bound. So we do a rigorous CPF design so that the control bound is satisfied. And then when we solve the QP online, we incorporate that control bound into our constraint.
I see, gotcha. So you still have guarantees, even though U is bounded in this case,
Yes.
because you didn't H in such a way.
Yeah, we design H in such a way, and that's a good point because if you have a control bound, then designing the CPF becomes a much more challenging problem. And there are ways of still incorporating those bounds into your optimization program that designs the CPF. So that's what we did here too. But it is definitely more challenging than when there's no control bound, because when there's no control bound, actually, go back to the definition of the CPF, like all you have to make sure is that this LGB value doesn't vanish. If LGB value doesn't vanish, you can take U, like a big enough input U, so that you can always satisfy this condition. And that's why for unbounded system, CPF design works beautifully.
Right. Actually, I have a question, like to be a little spicy, like, because how do you comment on, like for the bounded case to design a non-trivial H versus in reachability, you compute the V function, which one is harder? Because the whole argument is if CBF is it makes everything easier, but turns out you need to, you sort of, to me, you transfer the burden to designing a non-trivial H function. So could you comment on that? I think it might be helpful for a student to understand trade-offs.
Yeah, you got me. Yeah. So a really nice thing about CPF is, you ease the filter design part a lot. But actually, the hard part is in how we design the CPF itself. You got it correctly. And especially if we have a control bound, this becomes a non-trivial problem. And so there are works that do that. So here I use the quadratically optimal function. If we make this form a little bit more general to a polynomial function, there's like a positive polynomial function specific type of positive polynomial function called sum of squares. You can kind of formulate a sum of squares program, and then in that sum of squares program, you can impose this control input constraint as well. So that's one way. The other way is actually doing a reachability and use a reachability value function as a CPF. So reachability gives you a very systematic way of designing this value function that satisfy the safety constraint, satisfy the input constraint, the input bounds. So actually, control barrier function, if you have the input bounds, it can be seen as a function that is very similar to the reachability value function. And in fact, you can use the reachability-based formulation to compute the CPF. I see a question in the audience.
So I have a question on the comment of using the HA value function as a barrier function.
Yeah.
So that value function isn't necessarily differentiable everywhere. And since you need to differentiate the value function in order to compute the CBF, like in practice, like does that matter? Or like in what cases will it break the controller?
You got me again. So you're right. So the differentiability is definitely an issue in reachability, but it's something that we don't talk much about in the reachability community because it's really hard to tackle that issue. There are certain cases where we can still design a safe controller with even on the non-differentiable boundary using a notion of like subgradients. So supergradient or subgradient. There's a more generalized version of gradient for non-smooth function, and we can use that notion. But there are certain cases where it doesn't work, and it is case when like you use first start from start from smooth part of the value function, but then once the trajectory reach the non-smooth part of the value function, like the trajectory can get stuck on that sharp edge of the value function, and then it slides along that sharp edge of the value function. So if such things happens, then using that value function is unsafe. So actually, I have a recent paper that talks about this issue in a more rigorous way. So I'll kind of give you the pointer to that paper in the last part of my talk later. But I'm really actually surprised that you guys are asking these questions, because these are very important technical details, but like those technical details that I can not go into too much depth in this kind of tutorial-like session. So that's why I didn't talk about that, but you're definitely right. Yeah. Okay, really good questions. So let me recap CBF and reachability. So CBF, there are like three main approaches in the community for safety design. There are other approaches as well, but I think these three methods are the most kind of popular methods these days. The first two common theme of Hamilton-Jacobi reachability and contour barrier function is that they both use this kind of notion of a scalar function. In the reachability, this is the value function, and in the CBF, it's the CBF itself. If you think about what this scalar function captures, it captures our desired safety constraint and how our long-term effect of the dynamics would affect our system in satisfying this constraint. And these two information is combined together into this scalar function, so that usually the level gives us a measure of how far we are from the safety margin. And the gradient gives us information of to which direction we should drive our system state to ensure safety. And this is the core principle of both the reachability and CBF. In the reachability, the zero level set is our maximum safe set. In the CBF, our zero level set is our control invariant set. And the reachability, we use the gradient control. We use the gradient to synthesize the optimal controller. And in the CBF, we use the gradient control. We use the gradient to synthesize the barrier constraints that the control input should satisfy. Now, I'll not go into predictive control today because of the time limit, but predictive control doesn't use this notion of the circuit function. The predictive control formulate an online optimization problem that is a finite time horizon problem. And then it incorporates a set of safety constraints that works together to guarantee safety. But it's a finite horizon problem again. So if it's a finite problem, how do we ensure infinite horizon guarantee? And that's kind of the core design principle of the predictive control. So you impose besides our target safety constraint X, you impose a terminal constraint. So the trajectory at the final horizon should always stay inside our terminal set S. And this terminal set S is designed to be invariant. In this way, all the trajectory always have to end up in the control invariant set. And once it ends up in the control invariant set, from there, for the later horizon, you can always stay inside the set. So that's how you impose this indefinite horizon safety guarantee in predictive control as well. So if we sum up all this principle in each method, there arise two commonalities in these methods. So the first common aspect is that all this method use the notion of control invariance, and constructing a good control invariance set is the core design steps of all methods. So in the reachability, we explicitly construct the maximal safe set, the control invariance set from our value function. In the CBF, this is connected to how we design the CBF. In the predictive controller, this is connected to how we design the terminal set. The next thing is now we will start to think about how this model-based design will apply to scenarios where the model is inaccurate. So in all this design process, we use this dynamics information. Sorry, where's my cursor? So we use the dynamics F information. We use it in our reachability computation. We use it in our barrier constraints. We use it in our MPC dynamics constraint. So what if this dynamics is wrong, if this contains error? And all this method has their own extension to make sure that the design is robust to this error. So Andrea, have you taught the differential gain formulation?
Yeah, we've discussed that.
Yeah, nice. So yeah, so in the reachability, there's this formulation of instead of doing considering the problem as an optimal control, we consider a problem as a gain between the control and the disturbance. And in the CBF, there's a notion of input to state safety. And this ensures that our trajectory under a bounded disturbance stay inside some safe set with the additional margin. And in the MPC, there's a technique called constraint tightening. So we add up the uncertainty effects of the dynamics over our time horizon, and then make sure that the constraint is tightened and satisfy the safety even under those additive uncertainties. So robust design is the main mechanism of dealing with the error. And this principle will be extended to the data-driven design of the safety filters in my second part of the talk. Okay, so now we're in the second part. Andrea, how much time do you have more?
You have, let's see, like 35 more minutes in total.
Okay, I'll try to finish within 20 minutes. Yeah. So yeah, now why do we want to combine with data-driven methods if this safety filter design works very well? This model-based design will fail when model is wrong, as I said, and this more complicated robust systems these days, they involve a lot of uncertainty in the dynamics that is hard to model accurately. These days I work on the air taxis, the eVTOL vehicles, the aerial vehicles that involve change of configuration. And the aerodynamics this vehicle involves is really, really complicated. Like the lift profile and the drag profile is really hard to model accurately. So we need to kind of learn from data how they would behave. I would say the problem is slightly different from just learning the dynamics, because from the safety aspect, we not only have to learn the dynamics itself, the uncertainty in the dynamics, but we have to learn how the uncertainty affects our safety constraints. So that's kind of the core thing that is different from learning-based, control or learning-based dynamical models. Here we'll operate in a setting where, let's say, the true plant is described by this control fine dynamics, x dot equals fx plus gxu. But we have a mathematical model that is f tilde and g tilde. And we, of course, we would try to come up with a model that could describe the true plan as much as it can, but there will still be some gap between f and f tilde and g tilde. But this is an example of the filter I'll show you later, but this is just like a cart pole example, and the cart, we want to make sure that the cart doesn't hit the end point of this linear guide. That's our safety constraint. And we can quickly design a CBF-based filter for this system. And we use the mathematical model provided from the manufacturer. So this mathematical model is supposed to describe the system dynamics in high fidelity. But then if you deploy this filter, what happens is that for all 10 trajectories we rolled out, every trajectory actually exceeds the invariant set, the set S. So this means that the guarantee of the CBF constraint already is not working. It's not working because the model is incorrect. So later I'll show you that our modified filter design that is now model uncertainty aware can successfully fix this. So let's see how we do this. Oh, yeah, but the way it is, I worked on this with Fernando and Wonsuk and Bika. So we'll start with how the uncertainty affects our safety constraint. And in the CBF filter, we go back to the basics and we see that the barrier constraints incorporate the knowledge of our dynamics, right? The B dot is LFB plus LGBU. But here, the true Planck dynamics F and G is something we don't know. So in reality, when you design the filter, what we use instead is LF tilde B and LG tilde B. So that's the model-based estimate of our Lie derivative of the barrier function. So there's a mismatch between the actual Lie derivative and the model-based estimate of the Lie derivative. And those mismatched term will be called delta. And this is the uncertainty term that is affecting our safety constraints. So the main idea of this GP safety filter design is if we can learn this uncertainty term, and if we adjust this uncertainty term in our constraints, then we'll be able to recover the safety guarantee of the filter. For this, we'll use the Gaussian process regression. There are many benefits of using the Gaussian process regression compared to neural networks, and there are also downsides. But the benefit that we were excited about is that it is much more data efficient than the neural networks. And moreover, it provides a probabilistic bound of its prediction. So in the plot, you see that when it provides an estimate of where the target function would lie, it also provides a variance term together so that based on that variance term, we have a confidence of in what probability the true value will lie inside. So that is called the confidence bound of the Gaussian process regression. So once we collect the data and once we construct a GP model for this uncertainty term, with high probability of 1 minus delta, we have a guarantee that the true unknown value of this term will stay inside our mean value, mu, plus minus some constant times sigma, which is our standard deviation from the GP regression. So we can use this information to make sure that our safety filter or the constraint is robust to the error that the GP prediction can make. And in the CBF setting, the CBF value, having a lower value of CBF value is at more risk of violent failure, or it's closer to the safety boundary. So that's why we consider a lower bound of the CBF value. So with this GP confidence bound, we have a guarantee that our CBF value, the true CBF value, is larger or equal to our model-based estimate plus the lower bound of the GP prediction of the uncertainty term, with a probability of 1 minus delta. So based on this, we can construct a chance constraint for the barrier constraints. And when you do this, now we have to be careful with this because the original CBF constraint is a linear constraint in U. So that's why the original filter is a QP filter. But if we use a naive kind of a vanilla, like just GP regression, then this mean term and the sigma term will not contain this nice structure that is affine in U. So what we did in our work is actually like use the fact that the target function is also affine in U. The target unknown uncertainties affine in U. And then we exploit a specific kind of control affine structure in designing a specific kernel called affine dot product kernel, so that the resulting mean term is still affine in U, and the resulting variance term is quadratic in U. So if we use this specific kernel, then the mean term will look like this, and the variance term will look like this. So if we incorporate that into our chance barrier constraints, now we have this form where this term is affine and this term is quadratic, but with a square root. And that becomes a second order cone constraint. And second order cone constraint is still a convex constraint. So it'll render the feasible set to be a convex set. And so that the program, this filter program becomes a second order cone program, which is still a convex program. It slightly takes longer time than the quadratic program. But you can still solve this very fast with conic program solvers. So maintaining the convex structure here with the specific kernel design was a kind of the core part that makes this filter feasible to be deployed in the real world.
Jason, I have a quick question.
Yeah.
Does this choice of this kernel restrict what you can represent and therefore impact either the over or under conservatism of your chance constraint?
So the underlying assumption is that our target function has to be affine control. So let's say your true dynamics is actually non-affine control, then you cannot deal with that with this formulation. But as long as it's affine control, the kernel we choose actually is not the kernel itself. This is just the structure of the kernel. So there are hyperparameters of the kernel we can vary and we can tune. So so that we can make the constraints to be not too restrictive. So yeah.
Hey Jason, I have another question.
Yeah, go ahead.
Yeah. So seems like you're doing per step chance constraint. So how do we ensure the whole trajectory is sort of safe with chance 1 minus epsilon? Oh, sorry, 1 minus delta. Is there some extra procedures, or it's just yeah?
You're right. So this is a point-wise probabilistic guarantee. So for each point in the trajectory, you have a 1 minus delta safety guarantee, and for the entire set. And in order to guarantee recursive, safety guarantee, like the safety of the entire trajectory probabilistically, then you have to do something more. And the main case where the guarantee can break down actually is when we don't have enough data to characterize our uncertainty. So when we don't have enough data, the sigma term will become very large, which means for those specific control input and state, we don't know what will happen with our uncertainty. So if the trajectory ends up being there, then as I said, the trajectory will start to, actually this SOCP will start to become infeasible. And starting from there, we might lose our guarantee. So we have an extension of the work that does safety exploration online. And I'll not go into that today, but there's a paper on that. This is a journal extension of this conference paper.
Gotcha. Thanks.
Yeah. But you have to augment your data online. That's the key idea there. Yeah. Yeah, there's a question in the audience.
Yeah. In practice, how much data do you actually need to learn a good GP? Because doesn't the matrix inversion potentially make this kind of slow if you have too much data?
Yeah. So the downside that I didn't mention before is that the GP doesn't scale very well with number of data points. So I'll first show you the cartpool experiment here. So the experiments that I showed you before, you can see. So you can see in the plot. I have some additional plot here that the CBF constraints based on our model-based estimate. If you evaluate whether this constraint were satisfied from our data, it was actually not satisfied, and that's why you see that the CBF value dips below 0. And if with our GP-based safety filter design, we can see that the CBF again always stay positive. So we recover the safety guarantee by learning the uncertainty from the data. For this example, we collected 10 trajectories, and 10 trajectories all in, and that's why GP is actually quite powerful compared to data compared to neural networks. But for more complicated systems like leg robot, we have a 10D simulation of a leg robot in this work here. And for that 10D system, we had to collect 10,000 data, at least 10,000 data. And that's when the GP inference starts to slow down a lot because of the limited scalability of the GP. So actually, what we can do is we can analyze in the feature space of in the kernel feature space what data point could provide maximal information of what is the safe direction. And using that information, we can, when in the online inference, we can only select a subset of data. So we don't have to use all data. We only have to use, we can only use the data that is most relevant to characterize our safe direction. So that's actually the main idea behind this paper called like constraint guided online data selection. That alleviates significantly the computational scalability of the GP inference. So that's, again, something that I thought I didn't have time to go into. So that's I'm not going to the specific of that. But if you're more interested in that, so this two extension of this vanilla GP SOCP formulation covers the two questions you just asked. So one is online safe learning, which is if you face a state space, or like if the trajectory ends up in a region where you don't have enough data in your offline data set, then you can do an online exploration while guaranteeing safety so that you can augment that data and then guarantee a recursive feasibility. So that's one extension we did. And the other extension is because the GP inference scale doesn't scale well with the number of data, we do some online data selection to improve our GP inference time, and so that we can still deploy the GP SOCP filter online. So I think that's the wrap up of the GP SOCP filter we developed. But the main summary of this filter is that from the data-driven component that learns the effect of uncertainty to our safety constraint, we make sure that the CBF-based design is adapted and robustified with respect to the uncertainty in the dynamics and also the potential prediction error that the data-driven model can make. So that's the one-line summary of this method. And we'll move on to a more model kind of free-based safety filter design that instead of using the GP regression, using a neural network. Before that, any more follow-up questions about the GP safety filters? Okay. So this is a work I've done with an undergrad student, Dynamical, and he just graduated and he's applying for PhD. I'm not sure. I think he also applied for CMU. He's been one of the best undergrad students I've worked with. So if you have a chance to collaborate with him, I'll be happy to introduce him. And in this work we introduced a new notion of discriminant hyperplane, and I'll explain what this is. To explain this, let's go back to the first part of our talk. So we started our talk with reviewing what control invariance is and what Nagumo condition is on the boundary of the control invariant set to verify whether the set is control invariant or not. So when I describe this condition, I use this distance function h, right? The motivating question of this work is, do we actually need this function h to design safety filter? And all the design principle I kind of explained today, the reachability and the CBF, actually use this function h. But do we actually need it? It was the motivating question for me. And why I was asking this question is because for the same safe set, we usually have multiple valid certificate functions. And that actually bugged me for a while. And there's a example I'll show you that highlights this point. So let's say we verified some control invariant set and we want to design a CBF-based filter. And you will use this, barrier constraints to represent the safety constraint. And here, so here, this is a double integer example, like a simple 2D example. You don't have to worry too much about the dynamics. But let's say I use this specific choice of CBF, where the apex of this CBF is at the p value equal to 5. P is the position and v is the velocity of the particle. So in the phase portrait, the blue one is the zero level set of the CBF. And this is the initial state, and then the trajectory, the desired control signal starts from here, and then it converges to the equilibrium on the other side of the boundary, and then it will come back to our original starting point. And the reference control here again is intentionally designed to be unsafe. And like you use this design CPF, and you use gamma, let's say 0.2 or 1, and you can see that the CPF filter works successfully. If you just slightly modify your CPF, and then now let's say you choose a different CPF where the apex is at the origin, then with the same CPF representation, with the same barrier constraint representation, but only with a different CPF candidate, you'll have a quite different behavior of the safety filter. So here, since I intentionally designed the safety filter to be asymmetric, on the right side of the boundary, the trajectories are allowed to be closer to the boundary. But on the left side of the boundary, the trajectories are not allowed to be close to the boundary. But here, this how much you can stay close to the boundary is very symmetric, because the CPF here is designed to be symmetric, mirror symmetric at the origin. So this really kind of a little bit confused me, right? Like, oh, if you use different CPF candidates, even with the same kind of constraint and even with the same gamma, we get a different behavior. And actually, this is same for reachability, because reachability, we have a choice of choosing our distance function. So actually, depending on what type of distance function we choose, we have a different behavior of the optimal safe policy. So my main motivation of the discriminant hyperplane is, do we actually need this certificate function? And my answer was actually no. And that goes back to the Nagumo condition. The key insight here is that the Nagumo condition is still control of fine, and it actually doesn't depend on the choice of H. Why doesn't it depend on choice of H? So the constraint form that describes the Nagumo condition explicitly depends on H, right? So it looks like it depends on H. But if you define a set of control input that satisfy the Nagumo condition, this is a geometric condition. So it actually doesn't rely on H. So this set of H that satisfy the Nagumo condition only means that the control input should direct your vector field towards inside the set. But that's all it's describing. It doesn't depend on specific choice of H. So based on this, and based on the fact that for control of fine system, this condition is control of fine, we can abstract away H and think about how the actual safety constraint looks like. So we have our control input bound, like U, large U. And this Nagumo condition can be described as just some hyperplane-based constraint, AXU greater or equal to BX. So this is just a hyperplane that kind of is in our control input space and discriminates safe input from unsafe input. So for safe input, the trajectory, for safe input, the input will direct our vector field to inside the safe set, and the unsafe input will direct our vector field to outside of the safe set. So the definition is just that it is in the hyperplane that lies inside the control input space that discriminate this safe and unsafe input. And this is like the minimum structure that provides a sufficient condition for Nagumo's condition. So if no matter what H function we use, or even if we don't use such H function, the circuit function, if you can directly learn A term and B term, then that's all we need to design a safety filter. So that's how we came up with a new way of designing safety filter for this work. And the main theorem, the very informal statement, is that any discriminant hyperplane whose constraint described by this hyperplane is a sufficient condition for Nagumo theorem on the boundary provides a safe control law. And this is, you can almost consider it as a slight extension to Nagumo's condition, because Nagumo's condition only is defined at the boundary. So the first key feature is that this extends Nagumo's condition to the interior of the set. And it actually also generalizes the Hamilton-Jacobi and CBF-based safe control laws for control-defined systems. You can say that the reachability-based optimum control and the CBF barrier constraint is a specific instance of these discriminating hyperplanes. And the best thing about this is that it does not depend on any specific type of safe set representation. So in theory, it could even apply to, for example, predictive control-based formulation where you don't have explicit like distance-like function like H. And it can be learned without models through supervised learning and RL, like reinforcement learning. I actually won't go how we design the learning problem to learn A and B. And I'll refer to our paper. But what we did is define this notion of discriminating hyperplane and learn this through data. Learn this from a black box dynamical system without knowledge of the dynamics. And here are like the low dimensional examples. So like this is a 2D example, and there's a 4D example. And the SLDH here is the learned discriminating hyperplane safety filter, learned through supervised learning. And the thing I want to highlight is that in all these examples, we have different way of representing our safe set. So in the more in the jet engine example, we use the reachability to compute the maximal control invariance set to represent our invariance set. In the inverted pendulum, we use the CBF to represent the safe set. In the kinematic vehicle, we manually designed the invariance set and verified that it's invariant, but we manually designed it. So, you know, the nice thing about discriminating hyperplane, this applies to all sorts of representations of the invariance set. And one final demo I want to show is we apply this design to half cheetah. So half cheetah is actually a hybrid dynamics. It's not like control-affine dynamics per se, because it involves contact dynamics, but the continuous mode of the dynamics is still control-affine because this is a mechanical kind of dynamics described by the Lagrangian equation. And here, this is just like vanilla OpenAI GM benchmark. The maximize the travel distance is the performance task that the RL policy wants to learn. But now we will impose the safety constraints that the robot doesn't want to hit its head to the ground. And the PPO is the baseline method, the RL method that doesn't have any notion of the safety constraint, and it runs it successfully learns to run very aggressively. But you can see that in a lot of cases, the robot falls and violates this constraint. And compared to that, there's a PPO Lagrangian is a state-of-the-art safe RL method that combines the preference objective and the safety objective together with a Lagrangian multiplier. The kind of the caveat of this formulation is the Lagrangian multiplier has to be updated together with the policy. So that kind of induces some instability issue. And because of that instability issue, in a lot of time, we don't get a successful trained policy. Once we do get a successfully trained policy, what we see is that it's kind of successfully learned safety quite well. But then because of that, the performance policy is very conservative, and it walks really conservatively, very slowly. Now what we did is we trained the discriminating hyperplane safety filter with reinforcement learning, and we used that safety filter to filter out any unsafe action of the vanilla PPO that is learning the task. So the PPO learns the task, and it's the same PPO algorithm without adding any safety costs or things like that. It's just that the action, whenever the action is unsafe, the discriminating hyperplane will kick in and it'll filter out the unsafe action. You can see that because the underlying task policy is the same policy here with the PPO, it runs as fast as the PPO agent. Well, now you can see now here that it almost fell forward, but then the discriminating hyperplane safety filter kicks in, and then it prevents the vehicle from falling forward. And this is one thing nice about the safety filter-based framework, that it decouples performance from safety gain. But another nice thing here is that we successfully can train a safety filter using the notion of discriminating hyperplane without any knowledge of our dynamics, or even without the knowledge of or design or knowledge of our invariance set. So that's the key result I wanted to highlight from discriminating hyperplane, the recent work. But the key summary of this work is that this is a very good abstraction of the safety constraints for control affine systems that generalizes the CPF and Hamilton-Jacobi reachability and can be learned in a very kind of model-free fashion. So that's all of the main body of my talk. So if you are interested in further readings, so there was a question earlier about the differentiability and like the convergence. We actually covered a lot of subtle topics, like whether the reachability of alpha function will converge in infinite term version or not, or whether it will be differentiable or not, whether it can be used safely as contrary function or not. So this more tight theoretical linkage between reachability and CBF, I tried to establish that in the recent paper we published here. So if you're more interested in those topics, please read this paper. And there are also a lot of good, more general overview of learning-based methods for safety. So the first paper is the tutorial paper I wrote that I used for the first part of my talk, but there are also other good survey paper from other research group. So if you're, want to explore more various topics in this domain, I would point to these papers. My kind of final takeaways from this domain is that control invariance is there as a fundamental principle for all sorts of safety filter design. It is like when you think about how we are going to do safety filter design, this is the first thing we always have to think about. So there's the first message, and then the second message is that when you want to extend the model-based safety design to uncertain systems that involves error of the model, then making sure that the safety filter is robust to this error is essential. And data-driven models, it's not only important. It's not only important to learn, like quantify the uncertainty of the dynamics, but it's important to quantify how those uncertainty affects our safety constraints. And that's how I use the data-driven model in my GP-based safety filter. And finally, this is kind of wrapping up the discriminating hyperplane part, but geometric abstraction of the safety constraints could remove dependency on any specific choice of circuit function. And I think in general, this gives a much more intuition of how the safety filter works and how geometrically in the state space this filter would work. So with this takeaway, there's still like really many open problems in this research topic. So for example, one thing we haven't covered today is how these safety constraints hinder the system from achieving its task, or how we trade off between like multiple task objectives or multiple task safety constraints. So, like it's a very tricky topic because now we have to deal with multiple objectives and constraints. So there are really many open research topics that I want to keep exploring. And if you have more, follow-up questions or something you want to discuss, feel free to reach out to me.
Thank you so much, Jason.
Yeah, that's all.
Thank you so much. This talk was really, really lovely. We have a little bit more time for questions. Anything else on your mind?
Yep.
Wait, so back to the discriminating hyperplanes thing.
Mm-hmm.
So is the idea that given a control invariant set, that's like all you need. And then once you have this control invariant set, you can just learn these discriminating hyperplanes on the boundary. And then you can. So you mentioned something about this like hyperplanes thing being like even applied to like model free methods, but how do you ensure that you have a control invariant set without having a model of this stuff?
No, that's a good point. So how do we design control invariant set without model, right? Is that the question? Yeah. So actually in the paper we have a remark saying that certificate function is still useful to verify control invariant set. So the point I want to make here is that it's not that certificate function is not useful at all. Like certificate function is still useful as a way of representing this kind of control invariant set, but it's just that maybe it's not the only way of designing the constraint, like designing the safety filter, the control policy. So that's one thing. And the another thing is the supervised learning framework here that in the paper, we use the knowledge of the control invariant set. And that could be limiting because those control invariant set might have to be coming from some knowledge of model. But the reinforcement learning based framework that we made in the paper that we applied to this half-jira, we don't need any representation for control invariant set. We don't need to design it a priori. So we just learn implicitly through simulation. So even in the model-free setting, without any knowledge of the control invariant set, this works because we know that the safety filter has this structure. So it's like we derive the structure from our model-based control theory tool, but then we use that structure in a model-free way.
I have another question. So in the discriminating hyperplanes work, I'm assuming that you need coverage of both like positive and negative examples, like on either side of the hyperplane, right? To learn that boundary.
Yes. And that's yeah.
So my question is, okay, so that makes a lot of sense. If I have like a high fidelity simulator, I can do safely rollouts that show me evidence of both situations.
Yeah.
But let's say I collect data like in real time, right? Like I actually deployed a system. Most of the time, I'm not seeing safety violations. They're very, very infrequent, maybe, especially with a high performance controller. So do you have a thought of how this method would perform, or what even would an extension look like if you don't have a very balanced coverage of samples in each part of the hyperplane region?
Yeah. So whether like the question, I think it boils down to whether we do need unsafe data points or not, right? And I think it's an unsolved problem.
Yeah.
And especially for more data hungry methods like reinforcement learning, I think it's really challenging because reinforcement learning really needs exploration. So it really do need some unsafe data point. So the RL framework we established here, it definitely has limitation. It can be only applied to systems where you can simulate it with high fidelity kind of dynamics. So it applies there, but if you don't have a good way of simulating your uncertain dynamics, let's say, for example, air taxis, it's hard to apply this method. And for those methods, I would kind of go back to those GP based safety filter design, where we can still do some online safe learning while guaranteeing safety. So there we made a way of doing that. But for discriminating hyperplane, we still haven't figured out a way of learning safety filter without unsafe action. One more thing. So one final thing is, if we only have safe data, then we can consider a safety problem as a learning-based policy staying in the distribution of the data. And actually, like Katie, who is co-advised by Claire and Sergey Levin, did some work on that. I collaborated with her on that, and like there we used almost a reachability formulation to come up with the in-distribution invariant policy. So there you can kind of reformulate the safety problem as a staying in distribution problem. Yeah.
Thank you so much, Jason. Let's give one more round of applause.
Yeah, thank you everyone for awesome questions.